If you've ever accidentally dropped a heavy book on your keyboard.
Or a cat just walked across your desk.
Right, exactly. And you look at your screen and you just see this string of characters that looks completely chaotic. Just a random, jarring mash of letters, numbers, dollar signs, brackets, and slashes.
Yeah, it's just pure digital entropy to the average observer.
Totally. But to a specific kind of programmer, that chaotic keyboard mash isn't nonsense at all. It's actually a highly logical, incredibly powerful set of instructions. It's really a way of reading and filtering reality.
It absolutely is.
So today, welcome to our deep dive. We are unpacking the mechanics of regular expressions, and our source material today is this really great slide deck from an Introduction to Programming with Python lecture, specifically Lecture 7.
Yeah, the one covering regular expressions, or regexes as they're usually called, or the remodule if you're working in Python.
Right. So our mission today is to demystify these chaotic strings. We're going to bypass the basic, beginner tutorial stuff and really drill down into the architecture. We want to show you exactly what makes these strings the ultimate shortcut for parsing just endless seas of data.
Because it really requires a complete paradigm shift in how you conceptualize text. I mean,
How so? What do you mean by paradigm shift?
well, think about when you search for something in a standard document. You hit find and you type in a literal string.
Yeah.
Like you type Apple, and the computer just blindly scans for APPLE.
Sure, just exactly what I typed.
Exactly. But regular expressions shift you from searching for literal words to searching for structural concepts. You're actually defining the shape and the behavior of the data that you want to extract.
Okay, let's unpack this because that sounds awesome. And I promise you, by the time we wrap up this deep dive, you'll be able to read what looks like alien code.
You'll see the exact microscopic logic running under the hood.
Right. But before we can define those complex architectural shapes, we have to look at the fundamental building blocks, the alphabet of regex. And the most primal piece of this whole architecture is just a simple dot.
Just a period.
Yeah. And to anyone who has used basic search functions, you probably recognize the dot as a wildcard. It stands for absolutely any character you can think of, with one specific exception.
Right, the new line character. It won't match a line break.
Exactly. But think about the power of that dot for a second. If you use a dot in your pattern,
You are explicitly telling the computer's parsing engine, I do not care what occupies this specific byte of memory, as long as something is there.
yeah, it could be a letter, a white space, a comma, a number. It's just the ultimate expression of flexibility.
It really is.
It always reminds me of playing Scrabble. You know that blank wooden tile you use when you're totally stuck?
Oh yeah, the best tile in the game.
Right. You throw it down and declare, this tile is a Q today, or this tile is an A. The regex dot is basically the digital equivalent of that blank Scrabble tile.
I like that. But taking that Scrabble analogy a step further, the limitation in a board game is that you only have, what, one or two blank tiles?
Yeah, usually just two.
Right. But in data parsing, you might need to say, I want to accept any character, and I want to accept it an unlimited number of times until some specific condition is met.
Oh, wow. So you can just play infinite blank tiles.
Exactly. And this introduces quantifiers, which dictate the behavioral physics of those wildcards.
So if the dot is the blank tile, the quantifiers are the structural rules telling the engine exactly how many blank tiles it's allowed to consume at once.
You nail it.
Okay, so let's go over them. The source material outlines three main ones. We have the asterisk, the plus sign, and the question mark.
Right, so the asterisk or the star symbol demands 0 or more repetitions of the preceding character.
0 or more, so it could just not be there at all.
Exactly. And then the plus sign means 1 or more. It has to appear at least once. And the question mark means 0 or 1, basically making that character optional.
Okay, but here's where it seems like it gets dangerous. If we use our blank tile dot, followed by an asterisk, the infamous dot star,
Oh yeah,
we are basically telling the engine, give me absolutely any character and keep going infinitely.
And this is where careless architecture leads to systemic failure. I mean, if you deploy a dot star without clear boundaries, the regex engine becomes aggressively greedy.
Greedy, that's the actual technical term, right?
Yes. It doesn't just find a match. It races to the absolute end of your document, literally swallowing gigabytes of text in a single gulp.
Oh my God.
And then it has to work backwards. It's a process called catastrophic backtracking. It tries to work backwards to find the condition that satisfies the rest of your pattern. It can literally freeze an entire server.
That is wild. A single dot and a star can take down a server. So we use the question mark to tame that greediness, right?
Right. You can append the question mark to make something lazy instead of greedy, or you can use specific counting mechanisms.
Right, the curly braces. I saw this in the lecture slides. If you put a number in curly braces, like just the number m inside braces, you are demanding a mathematically strict number of repetitions.
Exactly, m times. No more, no less.
And if you use a comma, like m, comma n, inside the braces, it sets a rigid bounding box. It has to appear between m and n times.
Stepping back from the syntax for a second, though, the core philosophy here is moving away from brittle, hard-coded logic.
What do you mean by brittle?
Well, think about doing this without regex. To validate, say, a complex serial number, you'd have to write dozens of lines of cascading if-else statements, checking every single index of a string.
Oh, yeah. Like if character 1 is a letter and if character 2 is a number, that sounds awful.
It is. It's terrible.
Yeah.
Regex distills that entire process into, like, a dozen characters. It is elegant, mathematically sound, and highly efficient.
Highly efficient, sure, but as we just established with the whole .star server crashing problem, that efficiency is dangerous if it isn't fenced in. If you let wildcards run free, your pattern just matches the entire text corpus and becomes totally useless. So we have to build structural boundaries.
Yes. Fences.
Right, and the foundational boundaries are the anchors, the caret symbol, and the $sign.
Right, and it's important to understand that anchors don't match characters. They match positions in the void.
Wait, positions in the void? That sounds like sci-fi.
I mean, it kind of is. The caret matches the absolute start of the string, like the 0 index before the first actual character even begins, and the $sign matches the very end of the string, or the space, just before the final new line.
Okay, so this is how we prevent our search from just floating aimlessly. Like if I write carrot apple, it anchors the pattern. It will only flag the word apple if it is the very first sequence of bytes on the line.
Precisely. If the line says, "I ate an apple," the engine completely ignores it, because the positional requirement of being at the very start wasn't met.
So the anchors secure the perimeter. But inside that perimeter, you often need to restrict the wildcards themselves, because you don't always want the infinite possibilities of a dot.
Right. You usually want a heavily curated list of acceptable characters, and this is achieved using character classes, or sets, which are delineated by square brackets.
Okay, so inside those square brackets, you define the universe of acceptable options for that single character slot. So if I write bracket A, B, C bracket, that means match 1A or 1B or 1C.
Exactly. It basically creates a custom restricted wildcard.
Right. But here's a cool trick from the lecture. If you drop a caret symbol inside those brackets at the very beginning, so bracket, caret, A, B, C bracket, it inverts the physics of the set.
Yeah, it becomes a negation.
Right. It means match absolutely anything in the Unicode universe except an A, B, or C.
Which is incredibly useful.
Yeah.
But, defining those custom sets is powerful. But typing out, let's say, A through Z lowercase, A through Z uppercase, 0 through 9, and an underscore.
Every single time, you need to validate a basic username.
Yeah. It's tedious. And it visually clutter the architecture of your kind.
So regex solves this with built-in escape sequences. These are basically shortcuts that compile down to those complex sets under the hood.
We see these everywhere in production code.
Yeah. You have \-d, which instantly represents any decimal digit, \s, which captures any white space character, so spaces, tabs, line returns,
Right?
and \\w for a word character, which is all upper and lowercase letters, numbers, and the underscore.
But I'd argue the true brilliance of this design isn't just the shorthand. It's the binary toggle switch built into the capitalization.
Oh, yes. I love this part. For every lowercase shortcut that validates a class, there's an uppercase version that strictly excludes it.
Exactly.
I mean, it's so clean. If I already have sets with brackets, you might think shortcuts like \w are just giving us extra confusing things to memorize, but it's not.
Not at all.
Lowercase d accepts a digit. Uppercase d rejects any digit. Lowercase s hunts for whitespace. Uppercase s demands a non-whitespace character.
Right. It gives developers the ability to write highly complex, exclusive logic streams with literally 2 keystrokes, instead of a massive nested block of exclusionary code.
Okay, so we have our operators, our bounds, and our sets. But to truly master regular expressions, the lecture makes it clear we have to look past just the syntax.
Yeah, you have to understand the invisible machine that is actually executing these commands.
Because a computer does not look at a string of text the way you or I do. It doesn't see a word.
No, it processes a linear sequence of states.
So let's visualize that machine. The slide deck dives into logical grouping and finite state automata. which, if you've ever looked at a diagram of a state machine, it basically looks like a complex flowchart.
Yes, circles connected by directional arrows.
Right, so you might have a starting circle labeled Q1, and pointing right back to Q1 is an arrow looping around itself with a dot.
Which means the machine is sitting in state Q1, just eating characters, looping infinitely.
I picture it like a ticker tape feeding through a physical sensor. The gear at Q1 just turns, processing one character at a time, and it'll keep turning in place as long as the character matches the wildcard condition.
Right. But then on the diagram, there's a different arrow pointing outward, from Q1 over to a second circle, Q2.
And the label on that directional arrow is the @ symbol, and Q2 is marked as an accept state, so it has a double circle around it.
Yeah, this specific diagram from the lecture maps the deterministic logic of a rudimentary email parser.
Okay, so the computer starts at state Q1. It reads the ticker tape. Is the character an @ symbol?
If not, it follows the looping dot, effectively saying, this is valid username text, keep spinning.
Right. I liken it to a strict bouncer at a club or maybe a really rigid board game. You can roll a dot and stay on the Q1 space all day long. The computer is just happily consuming letters and numbers.
But you must eventually draw the @ symbol card to unlock the gate, shift the gears, and advance to the Q2 space.
Because the @ symbol is the exclusive key for that state transition.
Exactly. And once the parser shifts into Q2, it has reached an accept state. The structural requirement of your pattern has been satisfied.
So the underlying power here is mathematical certainty.
Yes. Finite state automata process text in linear time. They evaluate character by character, moving definitively through the states. By defining strict transitions, like requiring a dot wildcard loop, then an @ sign, then another loop, the computer is mathematically guaranteed never to accept a string that lacks that exact architecture.
It's amazing. It imposes rigid mathematical predictability onto chaotic human data entry.
And uses logical groupings to organize that math.
Right. The lecture covers things like the pipe symbol, the straight vertical line, to create an OR gate, either A or B.
And you use parentheses to cluster operations together, so the state machine evaluates them as a single coherent unit.
There's even the walrus operator, the colon equals sign, which allows the machine to evaluate an expression and simultaneously assign it to a variable in memory.
Which is so useful. And honestly, understanding that state machine is really what separates someone who just copies and pastes regex from Stack Overflow.
Which we've all done.
Oh, absolutely. But it separates them from an engineer who actually writes and designs it.
Okay, but you still need a way to interface with that machine, right? You need the programming toolkit to inject this logic into your actual applications.
Right, and in Python, that interface is the re-library, which you can find all the docs for at docs.python.org/3/library/re.html.
And the foundational functions they teach are re.search, re.match, and re.fullmatch. They all take the same primary inputs. You need the pattern you've built, the string you are interrogating, and an optional flags parameter.
But the architectural use cases for each function are vastly different. Re.search is basically your scout. It scans the entire ticker tape, looking for the first sequence of states that satisfies your pattern.
Just anywhere in the string.
Exactly.
Yeah.
Anywhere.
But then what is the actual difference between using re.match versus re.fullmatch? Like, why do we need both if they both check for patterns at the start?
This is where developers often introduce critical vulnerabilities into their code. Re.match forcefully anchors your pattern to the 0 index of the string. So it checks if the string begins with the required pattern.
Let's contextualize why that's a security risk. Say you are validating a user's input for an email address before injecting it into your database.
Right.
If you use re.match, the state machine checks the beginning of the string. It sees user@domain.com, hits the accept state, and returns a success.
Right.
But what if the user actually typed user@domain.com, followed by a malicious SQL injection script?
This is the problem. Re.match stops evaluating the moment its state machine reaches a final accept state at the beginning of the string.
So it completely ignores the malicious payload dragging behind it.
Totally ignores it. The string passes validation, the payload hits your database, and your system is compromised.
That is terrifying, and that is exactly why re.fullmatch exists.
Precisely. It essentially wraps your entire pattern in those caret and $ boundary anchors we discussed earlier.
Right.
It forces the state machine to evaluate every single byte of the input.
From the absolute start to the absolute finish.
That's right. If the pattern finishes, but there is still text left on the ticker tape, like our malicious script re.fullmatch violently rejects the entire string.
Absolute end-to-end validation. I love it. But Beyond validation, the toolkit also provides robust data manipulation tools like re.sub.
Oh, re.sub is incredible.
Right.
It functions as a microscopic surgical tool. It takes your pattern, locates it in a massive data set, and swaps it with a replacement string.
So if you are ingesting, say, 10,000 server logs a second, you
Yeah.
can use re.sub to automatically hunt down and redact any exposed API keys before the logs are ever written to disk.
Exactly. It's essential for data hygiene.
You also have re.split, which shatters a string into an array, not just based on a simple comma, but based on complex conditional patterns.
Hmm.
And re.findle, which acts kind of like a harvester, just ripping through a document and returning a clean list of every isolated substring that navigated your state machine successfully.
And you can alter the fundamental physics of the state machine using execution flags.
Oh yeah, the flags.
Yeah, so passing re.ignore case strips away the distinction between upper and lowercase letters. Re.multiline changes the behavior of the caret and $ anchors, allowing them to snap to the beginning and end of every individual line within a massive text block, rather than just the start and end of the entire file.
My favorite flag, though, has to be re.dodal, because it fundamentally upgrades our old friend, the dot wildcard.
Right, normally the doc stops dead the moment it hits a new line character.
But passing dodal removes that limitation. It allows your state machine to consume line breaks and span across multi-paragraph documents.
So when you combine the toolkit, the state machine logic, and the core syntax, you are truly ready to deconstruct complex production-level code.
Okay, let's put that to the test.
Let's do it.
Let's look at the final boss from the end of the slide deck. It is a massive, intimidating reject string designed to validate an email address.
It's a monster.
Yeah, if you're just looking at it, it induces panic. It looks like someone fell asleep on their keyboard. I'm going to read just the start of it. It reads, caret, bracket, AZ09 dot exclamation hash $%, and it just keeps going with punctuation.
Pure digital noise to the untrained eye.
Right. And then way further down, there's an @ symbol, and then more brackets and question marks and asterisks, and it ends with the $sign.
But let's apply the architectural principles we just established.
Right. We don't panic. We look at the structural bounds. The very first character is the caret. The absolute last character is the $sign.
So the architect of this pattern is demanding end-to-end full match validation. Nothing hidden at the start, nothing dragging at the end.
Step 1 complete. Now look at the first major block. Immediately after the start anchor, we have a massive character class set in square brackets. It contains AZ09, and a highly specific dictionary of punctuation marks. And sitting right upside that bracket is the +sign.
The quantifier.
Yes. So this entire intimidating first chunk just translates to the ticker tape must start with one or more valid alphanumeric or specific punctuation characters.
Which is just the local username part of the email.
Exactly.
So moving linearly through the state machine, what transitions us out of that loop?
Right there, perfectly isolated in the middle of all the chaos, is the @ symbol, the bridge. The state machine consumes the username, hits the @ symbol, and shifts gears into the domain validation phase.
Now, the domain phase is where this pattern elevates from intermediate to expert. Notice the heavy use of parentheses starting with $:. For example, parentheses, $:, bracket AZ, etc.
Wait, we mentioned parentheses are for logical grouping, but the outline notes refer to this specific syntax, the $:, inside the parentheses, as non-capturing groups.
Yes.
How does that actually alter the machine's behavior?
Well, by default, when a regex engine processes a group wrapped in standard parentheses, it assumes you want to extract that specific chunk of data later.
Okay.
So it allocates memory and saves the substring. But when evaluating a complex, multi-tiered domain like student.cs.university.edu, the engine has to loop through multiple subdomains separated by dots.
Oh, I see. If it captured every single one of those subdomains into memory, you'd be burning through system resources just to answer a simple yes or no validation question.
Precisely. Adding the $:: syntax explicitly instructs the state machine group this logic together to ensure the strict structure is followed, but do not waste RAM caching the output.
That is a massive optimization for high-throughput environments.
Yeah, it really is. And furthermore, you see the quantifier 0,61 inside curly braces within those groups.
Right.
This enforces the strict networking standard that an individual label within a domain name cannot exceed 63 characters. One starting letter up to 61 middle characters and an ending letter.
It's just stacked Lego bricks. A boundary anchor, a greedy but restricted character set, an explicit transition gear, and an optimized, memory-efficient loop for the domain. It proves that no matter how impenetrable code looks on the surface, if you understand the underlying mechanisms, the wildcards, the state machines, the boundary conditions, you can deconstruct it.
You can read the matrix.
You really can. You transition from someone who relies on trial and error to someone who commands the data with absolute deterministic precision. You define the exact parameters of reality your program is allowed to acknowledge.
Once you map the mechanisms, the syntax just becomes a tool.
It gives you a structural superpower. We started with what looked like a cat walking across a keyboard, and we uncovered a precise, elegant, and highly efficient logic engine that literally powers the backbone of digital communication.
It's pretty amazing once you wrap your head around it.
It is. So as we wrap up this deep dive, I want to leave you with a more abstract architectural question.
Okay, let's hear it.
We have spent this entire session mastering regex, a tool built on finite state automata, strict rules, and absolute deterministic mathematical certainty.
Right.
But we are currently rushing headfirst into an era dominated by large language models and probabilistic AI. These AI models don't parse text character by character through rigid state machines. They kind of just understand the contextual shape of data probabilistically.
That's true. They guess the next most likely token.
Exactly. So looking forward, will rigid, brittle, painstakingly handcrafted regex patterns eventually become an obsolete relic of the past?
Oh, wow.
Or when it comes to system security and data validation, will we always require the mathematically provable absolute certainty of state machine? Because what happens when a perfectly real human piece of data simply doesn't fit the rigid regex pattern that some programmer decided to write?
That is the million-dollar question.
It is. Something to consider the next time you write an exclusionary boundary. Thank you so much for joining us on this deep dive into the architecture of regular expressions. We will catch you next time.